what are we truly made of? I mean, really deep down. It's a question that humanity's grappled with for, well, forever.
Absolutely. From ancient philosophers just thinking it through to scientists today, it's a fundamental curiosity.
And today, we're doing a deep dive into someone who really, fundamentally, changed how we answer that question. John Dalton.
A pivotal figure. His work wasn't just chemistry, it was about how we even do science, how ideas evolve.
Exactly. So our mission today is to unpack really three key areas. First, his atomic theory, the thing that basically launched modern chemistry.
Revolutionary stuff.
Then we'll get into something more personal. His own research into color vision, because he experienced it differently.
Which is fascinating in itself, turning a personal quirk into scientific inquiry.
And finally, his work on gases and meteorology. He was obsessed. We'll see how his observations, his thought experiments, they changed everything. But also how even giants like Dalton can hold ideas that will turn out wrong.
Which is a crucial part of the scientific story, isn't it?
Totally. So let's kick things off. What can a Quaker schoolteacher, a weatherman, and someone who saw colors differently teach us about discovery?
A lot, I think.
Okay, so before Dalton, understanding matter, it was often more talk than anything else, right? Like the ancient Greeks, Democritus, Leucippus, they had this idea of atomos, indivisible bits.
They did, yeah. But then you had someone like Aristotle, hugely influential, arguing for continuous matter, that you could just keep dividing things infinitely smaller, no fundamental particle.
And relying on just discussion, well, it didn't get science very far, did it? How do you prove anything?
Exactly. That's what our sources really highlight. Progress was slow because there wasn't that experimental rigor. You needed a way to test ideas. Things started shifting later, with people like Robert Boyle pushing for proper experiments, moving away from alchemy.
Right, more doing, less just theorizing. But the real setup for Dalton involved two other key players, didn't it? Lavoisier and Proust.
Absolutely critical. Lavoisier gave us the law of conservation of mass matter isn't created or destroyed. Huge.
And Proust.
Proust came along with the law of definite proportions. Basically, elements combine in fixed ratios to make compounds. Like water always having the same proportion of hydrogen and oxygen. These were the hard facts Dalton had to work with.
So Dalton, this Quaker school teacher, also a keen meteorologist, he sees these laws, these numbers.
And he connects the dots. He was doing a lot of work with gases, specifically nitrogen and oxygen. He found they could combine in different ways to form 3 different oxides: nitrous oxide, nitric oxide, nitrogen dioxide.
Yep.
And he noticed the ratios of oxygen combining with nitrogen were simple whole numbers. One ratio, then double that, then maybe triple. That led him to the law of multiple proportions.
Okay. So definite proportions for one compound, multiple proportions when elements form different compounds.
Precisely. And he realized this only makes sense if hydrogen, nitrogen, oxygen, all elements are made of tiny indivisible particles, atoms.
And that's the core of his theory, laid out in his big work, New System of Chemical Philosophy in 1808. Can you sort of walk us through the main points?
Sure. It boils down to a few key ideas. 1, all matter is made of atoms' tiny indivisible particles.
Indivisible. Good.
2, atoms of the same element are identical, same size, same mass. Atoms of different elements are different.
Makes sense.
3, atoms can't be broken down, created, or destroyed. Chemical reactions just rearrange them.
Right, like Lego bricks.
Kind of, yeah. 4, atoms combine in simple whole number ratios to form compounds, not, 1.5 atoms of oxygen with 1 hydrogen.
Got it. Whole numbers.
And 5, chemical reactions involve combining, separating, or rearranging these atoms.
So for chemists back then, this must have been like getting a rule book after playing a game with no instructions.
Absolutely. It gave them a framework. Suddenly, those fixed mass ratios from Lavoisier and Proust had a reason. Reactions weren't just mixing stuff. It was atoms combining in predictable ways. It turned chemistry into a quantitative, predictive science.
A massive shift. But, like we hinted, science isn't always perfect first try. Tell me about his rule of greatest simplicity.
Ah, yes. That's a really good example of how science works. Dalton didn't have all the tools we have now. So when 2 elements made just one compound, he assumed the simplest possible combination, 1 atom of each.
Like water being HO.
Exactly. He proposed water was HO. Logically, it was the simplest explanation. Turns out it's HO. We needed Avogadro's work later to figure that out.
Okay.
But Dalton's assumption, even though wrong, was a starting point. It was a testable idea that spurred further investigation. He did a lot of these thought experiments, picturing atoms combining, which helped guide his lab work.
So even the bits he got wrong were useful, in a way.
Definitely. It highlights that scientific progress involves refinement and correction.
Okay, so bringing this to today, Dalton gave us the atom, fundamentally changing chemistry. But, and this is fascinating, our sources say he still had a kind of continuous view of matter. He thought atoms were packed right up against each other, no empty space.
It's a bit of a paradox, isn't it? He proposed discrete particles, but couldn't quite shake the idea they were all touching, maybe held apart slightly by forces.
Why? Why hang on to that?
Well, it seems he was still influenced by older ideas, maybe Newtonian physics, thinking about forces between particles. The idea of atoms existing in empty space was maybe too radical a leap at that point. And apparently, this view actually held back atomic theory for maybe 50 years.
Wow, 50 years.
Yeah. It shows how hard it is to break from existing ways of thinking, even for brilliant innovators. And it links to something students still struggle with today, right?
How so?
Thinking that, say, a single atom of copper is actually reddish-brown, or that the atoms themselves get bigger when you heat something up.
Ah, right. Projecting the bulk properties onto the individual particle.
Exactly. It's a common hurdle understanding the difference between the microscopic particle and the macroscopic substance. Dalton wrestled with a version of that too, it seems.
That's a perfect transition, actually, from the nature of matter to how we perceive it. Let's talk about Dalton's own vision. He and his brother saw colors differently. They confused reds and greens, pinks and blues.
Yeah, imagine seeing the world like that. What's remarkable is that Dalton, being Dalton, didn't just live with it. He studied it scientifically.
Right. He published that paper in 1794, Extraordinary Facts Relating to the Vision of Colors, the first real scientific look at color blindness.
The very first. And he came up with a hypothesis.
Which was?
He figured the fluid in his eyeballs, the vitreous humor, must be tinted blue. He thought it was acting like a filter, blocking certain colors, specifically reds and greens, from reaching his retina properly.
Okay, a physical explanation. Makes sense for the time. And he was so committed, he actually left instructions for his eyes to be dissected after he died to test this idea.
He did talk about dedication to the scientific method. So after he passed away in 1844, they did the examination.
What did they find? Was it blue?
Nope. The report came back. His vitreous humor was perfectly colorless.
Oh, wow. So his own theory was disproven by his own experiment, essentially.
Pretty much. From beyond the grave, the irony is quite something.
But the story doesn't end there, does it? Science marches on.
It really does. Fast forward 150 years to 1995. Scientists got hold of preserved tissue from his actual eyeball.
No way.
After all that time.
Yep. And using modern DNA analysis, they found the real reason. He was missing the gene for the medium wavelength photopigment, the green-detecting cone cell pigment in the retina.
So he was a deuteranope, red-green colorblind, diagnosed definitively a century and a half later.
Exactly. It's an incredible example of how new technology can answer old questions with precision Dalton couldn't have dreamed of.
And the condition even became known as Daltonism for a while, right? It still is in some places.
It is a fitting tribute, really, to the man who first studied it scientifically, prompted by his own unique way of seeing the world.
Okay, so we've had atoms, we've had color vision. But Dalton's curiosity didn't stop there. He was also deeply into meteorology, like really into it.
Oh, absolutely. He kept a weather diary for, 57 years? Recorded over 200,000 observations. That's commitment.
That's a lot of weather watching.
Yeah.
How did this connect to his other work, particularly with gases? Well, his atmospheric studies definitely fueled his interest in gases. It led him to formulate Dalton's law of partial pressures around 1801.
Remind us what that is again?
It basically says if you have a mixture of gases that don't react with each other, the total pressure is just the sum of the pressures each gas would exert if it were there alone.
Okay, the pressures just add up. And his atomic thinking played a role here too.
It did. His explanation, though not quite right by modern standards, was based on his atomic ideas. He thought that in a mixture, only atoms of the same kind repelled each other. Different gas atoms ignored each other.
Interesting idea.
Yeah, he thought this repulsion between atoms stopped heavier gases from just settling at the bottom, again, trying to link the macroscopic behavior to invisible particle interactions. He also independently figured out what we now often call Charles's law, that gases expand equally with temperature under constant pressure.
So his meticulous weather data wasn't just data for its own sake. It fed into these fundamental laws about gases.
Exactly. It helped move meteorology towards being a more quantitative science, less just folklore. It really shows the breadth of his scientific mind. It's about atoms, vision, the atmosphere, all subject to the same rigorous observation and search for underlying principles.
So pulling it all together, John Dalton, a self-taught Quaker, incredibly curious, leaves this massive legacy. Atomic theory, the foundation of modern chemistry.
Undeniably.
Pioneering work on color blindness, sparked by his own experience.
Laid the groundwork for understanding vision differences.
And fundamental contributions to our understanding of gases and meteorology.
Yeah, a truly versatile scientist. His journey really underscores that science isn't this neat, straight path. He had brilliant insights, but also made assumptions that needed correcting later, like the indivisibility of the atom or his eye fluid theory.
Right. His work paved the way for people like J.J. Thomson discovering the electron, Rutherford the nucleus, Bohr the quantum model, building on and refining Dalton's foundation.
Exactly. It's all about that continuous process of inquiry, building, testing, sometimes being wrong, but always moving understanding forward. Even the wrong bits pushed science along.
It's a powerful reminder. So for you listening right now, think about this. Dalton's simple assumptions, like HO for water or the blue fluid in his eye, seemed logical then, but were overturned. What ideas do we hold today? Things that seem completely obvious that future discoveries might show are incomplete or even fundamentally wrong. What stands out to you about this whole process, the back and forth, the insights and errors that define how science actually happens?